This is a video lecture to go with the notes for week 10, which covers Chapter 5 for the A to D and D to A, and Chapter 6 for the SCI. Now if you watch this YouTube video here, it takes you through the process of how the successive approximation A to D works. And each A to D has a V reference low, in this case 0 volts for this particular one on this page, and V reference high, which is 128 volts. Now if we want to figure out which voltage is generated by this particular binary set of numbers here, this is going to be 1/2 plus 0 quarters plus 1/8 plus 0 sixteenths and so on. And when we take that number and multiply it by 128, we're going to see what voltage this particular digital value here represents. And we can see that in this calculation here. 1/2 plus 0 quarters plus 1/8 and so on. And when you do the math, it works out to 80 volts in our particular case here. Now this is the kind of question you're going to be asked on a test. You're going to be given a number like A0 or C0 or D0 or something of that nature. With V reference low and high, it could be 0 to 64, 0 to 128, 0 to 256, where the calculations are going to be very easy because you're going to have to do these without a calculator. This page actually goes through what we did in Lab 7. In Lab 7, we put an 82 into address 21. We put a 0C into address 23. What that did was it set a 0082 into our baud register, and what that did was it set the serial shift rate from the transmitter to the PC screen and from characters being typed on the PC keyboard to the receiver. Now whatever number you put in here sets a serial shift rate for both of these at the same time. And this 82 sets the serial shift rate to 9600. And that's important because over here we have hyperterminal controlling these two on our PC, and it's expecting things to be shifted to the screen at 9600 and shifting stuff from the keyboard to the receiver at 9600. So whatever we do, we have to make sure this is set to the right number to be able to communicate properly with hyperterminal at 9600 baud, and that's what the 82 does. The second thing we had to do is put a 0C here, because one of the things you'll find on these devices, this transmitter and receiver are completely disabled when you first power them up to save power. And so what you want to do is enable these two, because if you don't enable it, it can't shift anything. The transmitter won't be able to shift anything to the PC screen, and the keyboard will not be able to shift things to the receiver. So the 0C here enables both the transmitter and receiver so that it will be able to act properly. And so two things we need to initialize the SCI is to actually set up our baud rate and to set our control register 0C to enable both of these, and then once that's done, then the initialization of the SCI is complete. Once we've done the initialization, then we can actually start sending characters from our CPU here to the screen. Now the way we did it here was we had to put a 00 here to force it to read the status register, which is this thing, and then we were able to put a number here, and then it would actually shift that number to here. So putting a 00 here would read the status register, putting 41 here would put the 41 into the transmitter, which would then automatically start shifting this out at 9600 baud to the PC screen. This kind of transfer here from the accumulator to the transmitter is a parallel data transfer. Parallel data transfers happen in a fraction of a microsecond. But once it's done this parallel storing from the accumulator to the transmitter, from the transmitter to the screen, it's not doing parallel anymore, it's doing a serial shift at 9600 baud. And it takes 1042 microseconds from the time it's stored here to actually appear on the screen. So the parallel data transfer happens in a fraction of a microsecond. This takes 1042 microseconds to do the shifting. So as you can see here, there's going to be a bit of a bottleneck from storing to actually transmitting it to the screen, and we have to wait until the transmitter data register here is empty. And that's what this TDRE bit here is. Once you store something into the transmitter data register empty bit goes to 0, saying it's not empty. You better not store anything else to the transmitter because it's in the process of shifting. When this TDRE bit here goes to 1, it means that this has been completely shifted to the screen and it's safe to send another character here. So one of the things we have to do is check our status register before we actually store something from the accumulator to the transmitter to have it go to the screen. Once the 41 has been stored to the transmitter from the accumulator in about a fraction of a microsecond, Let's take a look at how it goes in a shifting operation from the transmitter to the PC screen. The PC screen here is a receiver, and any receiver will be sitting at idle high, in our case 3.3 volts, and it's going to stay there until some information is going to be shifted from the transmitter to the PC screen here. But it doesn't shift out the 1 or the LSB first. What it has to do is to get the attention of the receiver, it has to go from the idle condition to the low condition and hold that for 1 bit time to wake up the receiver, in this case our PC screen. What that does internally here is generates an interrupt, which will be covered in a future course, but the concept is, since this is asynchronous, the receiver here has to know when information is coming, and it knows that when the transmitter sends it a start bit, a low bit here for 1 bit time, and holds it low, that's enough to wake up the PC screen or a receiver, and then start taking the least significant bit to the most significant bit, which is this. And then at the end, what it does is the transmitter will then set this bit high for 1 bit time, called a stop bit, which will give the receiver, in our case the PC screen, time to actually put it up on the screen before the next character arrives. So anytime the transmitter wants to send something to the screen, it sends 10 bits, the 8 data bits plus a start bit plus a stop bit, and that's a 10-bit format. Now when we hit a character on the keyboard, what the keyboard does now is it's the transmitter, if you like, and over here our receiver is a receiver register. So it's going to send a start bit again. So the receiver here is at an idle high condition. The PC keyboard sends a start bit, which wakes up our receiver here. And then once it receives that, it's going to send the least significant bit here to the most significant bit, least significant to most significant here, followed by the stop bit, which is going to give it 1 bit time and deal with it. So again, 10 bits, but notice in this case, the start bit, least significant, start bit, least significant, it's going in the opposite direction. Now once it's here, once it's received our capital letter A, the RDRF, which is receiver data register full, goes from a 0 to a 1, saying that there's something in the receiver that came in from the keyboard. When you take a look at the receiver, once you hit a character on the keyboard and it's shifted in, then the receiver data register full flag will go to 1. And how does it go to 0 from a 1 saying it's full? Is when you load what's in here into the accumulator, then this will go from a 1, which was full, to a 0, which is not full. But it's still got the information in here, but it's not full of new information. In fact, it's not going to go to a 1 here again saying it's full until you hit another character and it's completely shifted in. Let's do a quick review of what we learned so far. To initialize the SCI, we have to put an 82 here to set the serial shift rate from the transmitter to the PC screen at 9600 baud. And any character hit on the keyboard will then also be shifted into the receiver at 9600 baud. So the baud register sets the serial shift rate for the transmitter and the receiver. The control register, putting 0C here, enables the transmitter and receiver, because without those being enabled, no shifting will happen here or here. The transmitter, any character stored to the transmitter is shifted to the PC screen at the set baud rate that you've got here. Any character hit on the keyboard will be shifted to the receiver at the baud rate that's set here. If you take a look at the control bits here, TDRE, if it's equal to 1, means the transmitter data register is empty, which means this character has already been shifted to the PC screen. If TDRE is equal to 0, which means the transmitter data register is not empty, that means that it's in the process of shifting, so don't store anything to the transmitter here. Also over here, what you're going to find is we have RDRF. If RDRF is 1, it means the receiver data register is full, because whatever character you had has been shifted in. To be not full, you have to load this into the accumulator for a receiver data register full being 1 to be now 0, to saying it's not full of new information. You notice here that the transmitter, SCI2D, and the receiver, SCI2D, both share the same physical address. So if you do a load from that address, it sets the read-write line here high, which accesses the receiver. If you do a store operation, that sets the read-write line low, which accesses the transmitter. Now let's take a look at how we check the TDRE bit and the RDRF bit to see if it's safe to send something or if something has come in. One of the things you're going to find that SCI2S1 is our status register, which contains TDRE and RDRF. TDRE is the most significant bit here, and down here this is RDRF. So what we have to do is wait for the transmitter data register to be empty. So what we're going to do is take our complete SCI to S1 and end it with this to separate out the TDRE bit. Now if TDRE is a 1, that means that this number here that you're ending is going to be 80. And while not 80, will give you 0, and it's going to drop down here because when the transmitter data register is empty, it's okay to actually take this value of output and send it to the transmitter. So this is transmitter gets output. However, if this bit here is a 0, then the answer is going to be 0, and while not 0 means while 1. So it's going to wait here until the transmitter data register is empty, which is about 1 millisecond, and then it's going to say the transmitter is going to get whatever value we wish to send out on it. Now down here for the RDRF, this is the RDRF bit here. And it's a little different because a lot of times you're not going to receive anything. So what you want to do is use an if statement. So this is RDRF here. So again, you're ending it with this number. So if the RDRF is 0, it means nothing came in, and it's going to give you a 0 here. It's just going to go down and fall through. However, if something came in, it's going to give you something that's not 0, and it's going to say input equals SCI2D. On this side, this is the receiver. So some variable is going to get what's in the receiver. So on this side, this is transmitter. On this side, this is receiver. So as we said, the read-write line, the transmitter and receiver share the same address. Storing to this address sets a read-write line low. Storing sets a read-write line low, and that accesses a transmitter. Loading sets a read-write line high, accessing the receiver. So they're different physical addresses, but you can't load and store at the same time. So loading accesses the receiver, storing accesses the transmitter. And one of the things you can see here, this is transmitter on this side, this is receiver on this side. So when you do this, it's really saying transmitter gets what's in the receiver, which is a way of actually making it into sort of a typewriter thing. Now over here we have SCI video. Now this is not for our particular board. This is for a 32-bit microcontroller. And there are a couple small issues that are different. Number one, the number used to set the baud rate at 9600 baud is different, and instead of using hyperterminal, they're using something called PuTTY. But most of the rest of the details are again the same as we've just gone through. Arduino-like functions that use the SCI2, SCR_clear, set cursor, print, SCR write, and KB getchar. Now in your project, what you're going to have to do is a lot of SCR printing and SCR set cursors to set stuff up. When you get to the last part of the project, you're going to have to get a character from the keyboard and see if it's a 1, 2, or 3 to reset those particular counters. If you wish to wait until a key has been pressed on the PC keyboard, you would say get a character from the keyboard, put it in A, and if it's equal to 0, stay there. Or if you want, you can say get a character from the keyboard. If it's not 0, then do something and just continue on. So you can either sit in a loop or you can just quickly check and then go on here. Now a couple things, when we set up our baud rate, the concept of baud is really the number of bits per second sent through the system, as long as you're doing complete computer-to-computer communications without a network. Now this is POTS, which is our plain old telephone service, and what you're going to find is that most systems, when you're communicating computer to computer, actually use a modem, a modulator, demodulator to actually send things through some sort of network system. And voice bandwidth for us is 4 kilohertz, which is pretty cool. And what you're going to find is that when you're going through the plain old telephone service, it only supported 4 kilohertz bandwidth. And the modem actually was able to use something called compression and decompression, because if you're sending stuff serially through here from modem to modem and connecting up to the computer, one of the things you find is that's very slow. So when you have a network and you don't have computer to computer connection directly and you're using a modem to go through a network, you have something called codecs. Codecs are compression decompression algorithms, and these give you faster throughput. It's like zipping something, sending it, and unzipping it at the other end. And that's what a codec or compression decompression algorithm does. It allows you to get further throughput. So if you're looking at a network, when you're looking at the term baud rate is going to be different going through a network than it is just going computer to computer without a modem and without any kind of service like we've got here. So in our particular case, we have no network. We're going computer directly to computer, and for that specific case, only for uncompressed data flow, baud is the number of bits per second.